He will be speaking, so. And there's also water for speakers.
Oh, yeah. Thank you.
Welcome.
I forgot. I still have Karen's name on. We can start. So, hello everybody. My name is Bandan. I'm a software engineer in the virtualization group at Red Hat. And so this is a talk about nested virtualization. So Drew spoke about x86 extensions and a little bit about how KVM works for x86. This is going to build on top of that and give us an introduction to the topic. So this it's a somewhat modified version of a presentation we did at KVM Forum last year. Yeah, but this is more focused on an introduction to the topic and more on some of the features that we have added recently to improve nested virtualization performance. So that's the outline, the usual introduction at first. And then we are going to go through some use cases where things don't work. Definitely that's not an exhaustive list, but it's based on past experiences when things did not work and how you could change your configuration so that you could mitigate the problem until the real bug is fixed. And then nested virtualization, as far as implementation is concerned, is applicable both to Intel and AMD. It works on both. But this presentation is mostly focused on Intel because most of the hardware features that have been added recently is on Intel and most of the code changes as well. But I do have a slide on AMD just to give you just a status update. Then we go through some of the changes that we have added for KVM with support from hardware as well to improve performance. And then we have the wrap-up that just tells you the current state and future work. I also have a last slide on references to links to past presentations on nested virtualization. So if you are interested, you could follow them as well. So what is it? So as the name says, it lets you run a hypervisor inside a hypervisor, or top, if you will. And in the figure to the right, you could see we have, I have a pointer. We have KVM, the hypervisor that's actually running on top of hardware. And KVM is a hypervisor, and then KVM tries to launch some guests, which is, as you can see in yellow, Windows, Zen, and ESX over here. And we all know that they also happen to be hypervisors themselves, so they might want to launch their own guests. And that's where the nested virtualization infrastructure lets the yellow boxes to use the virtualization extensions, the x86 extensions, to actually launch their own guests. So you get a performance improvement by not actually having to emulate stuff and rather using the hardware extensions. And we try to, if you try the layman's approach, you could look at the Russian dolls image and you could think of it as, the inner level dolls are kind of the upper level hypervisors, the nested hypervisors. They are constrained in resources, so they are smaller size, but at least theoretically, they should have the same functionality as the hypervisor that's running on top of hardware. And also, it's important to note that although the functionality is the same, we should also remember that, and rightfully, I think the yellow boxes could think that they are actually running in a hypervisor environment as if they're running on top of hardware. But it's not exactly the case because the hypervisor environment that the yellow boxes see is actually controlled by KVM here, the red box. So that understanding will probably help us in our configuration, or when things don't work or why something isn't working. So that's the introduction that I would give. But following up on Drew's footsteps, if my mom is gonna describe nested virt, probably that's how she's gonna describe this. Okay, that is a bad joke. Oh, you had a question?
Is 4 levels the deepest you can go, or can you go 5 levels?
I'll get to that later. We have that. So in terms of uses, so a lot of the use right now is just, people trying out just for fun. I don't know of any serious uses that this thing is seeing, but we do have a lot of interesting talk, a cloud vendor could have an edge because it's giving the users the ability to run their own hypervisors. I don't know if there's any cloud provider that's doing it right now, though. But anyway, then in terms of testing, you could think of testing attack vectors on hypervisors. You could say that you could try that running in a nested environment, so that you are doing it in a safer environment if you're not doing this on top of hardware, rather than if you're running the hypervisor on top of hardware rather than running it in a nested environment. And these are some of the things that I just heard from people, and it's not something I know definitely are the users. Okay, interoperability is basically if you think of some legacy virtualized environment that someone has, a big corporation has maybe, and they want to make changes so that this environment actually runs on a new hypervisor. But rather than doing that, they could probably just move the whole thing, the whole hypervisor they have, to nested environment, and probably it would save some time. So these are some of the uses. So these two slides are probably redundant because Drew has covered them, but nevertheless, I'm just going to quickly go through them. So this is the building block of x86 virtualization, and we need to know about this before we can jump to nested virtualization. So it's a data structure that is defined by the hypervisor, and then that's loaded onto the CPU memory, and the CPU uses this data structure to decide how to launch the guest and when to exit from the guest, and run the host to do some bookkeeping and whatnot. And these are the logical fields, and as you saw in the last presentation, the names are pretty straightforward. These are just the logical sections. So the guest state area has the guest state, the host area has the host state, and so forth. The exit information fields let the hypervisor know why an exit occurred and what to do for that. So with that information, we can look at how nested virtualization works. So in here, we have hardware on top of which KVM is running, which is our level 0 hypervisor. And KVM is going to use a virtual machine control structure, or VMCS. It's using VMCS 01. So the hypervisor is going to create this VMCS and launch Zen. Now, Zen, being a hypervisor itself, might want to launch its own guest. So Zen creates a new VMCS. This is VMCS 1.2, and uses that to and would attempt to use it to launch its guest. But when it loads this, tries to load this VMCS, since Zen itself is actually a guest for KVM, that the loading process actually gets trapped by KVM, and then KVM is actually going to create a new VMCS from information from VMCS 1.2 and also from VMCS 0.1, and create this new VMCS called VMCS 0.2. And then it's going to use this VMCS to launch a new guest, which is Linux here. But the difference being that this guest is actually being run on behalf of Zen. So from the perspective of Zen, or L1 in this case, it thinks that it's actually running L2 or Linux. But the reality is that this is the guy who's actually taking care of doing the hard stuff. So, and at any point of time, assume that the processor is in Linux at the top, and an exit occurred, an interrupt happens. External interrupt may be a keyboard press or something, and so the processor jumps back to KVM, and the hypervisor there, KVM itself, will decide what to do with that event. In some cases, the hypervisor might just handle it itself and then jump back to L2 or Linux, or in some cases it may handle it, or it may need to inject something to L1. So then it's going to use VMCS 01 again to run this L1 here. And then at some point, Zen again is going to resume the guess that it thinks it's running. So we jump back again to L0, and then L0 is again going to run L2 on behalf of L1. So it's kind of going back and forth, but it's not as slow as I made it appear. But anyway, that's how both L1 and L2 make progress. That's how both of them move forward, because the processor is switching between both of them and executing both of them. So on Intel, nested virtualization is disabled by default. The assumption is that it's not stable enough. If you want to enable it, you have to load KVM Intel with nested is equal to 1. And that's the first step. The next step is that you need to, QEMU needs to provide a CPU module that has the VMX flag. So you could either use CPU host that makes, just copies over the host CPU flags, including VMX, assuming that, of course, your CPU has VMX, which is probably the case. Or you could also use one of the known, the QEMU CPU modules like Sandy Bridge or anything else, and just explicitly, add the VMX flag. And that's how, the guest is going to see VMX, because if the guest doesn't see VMX, then KVM inside, in the inside guest won't be able to, initialize, because it relies on that. So, and then you could actually check in proc CPU info inside the guest that, the VMX flag is present. Just a configuration example. So we have, 4 host CPUs on top of which KVM is running, and then here I gave, on the QEMU command line, I gave CPU Sandy Bridge plus VMX, and I have, so QEMU is going to model 2 CPUs for me, which are Sandy Bridge, and that's being used to run level 1 here, and so level 1 sees Sandy Bridge CPUs. Now QEMU inside level 1 is going to run with CPU Nehalem, so the top most level 2 guest is going to see a Nehalem CPU, just one, and just a simple setup. Of course, you could make it more complicated. So the next few slides cover situations where things don't work, and the reason I had the previous slide is because I wanted to just give you a quick, overview of the CPU models. So we have these, QEMU has these CPU models, and they try to emulate their hardware counterpart. And we don't advertise all the flags, only those flags that actually make sense. There are some that probably cannot be emulated. But sometimes there are also, new flags that are added to the processors, and they might interact in unusual ways just because of bugs maybe, or because of features that are not implemented. In those cases, your nested virtualization setup might not work. So, and this is a very common problem. I mean, everyone sees this once in a while who has, tested nested virtualization. So, one quick way to get around this is, try disabling something that you think is causing some issues. Like on older processors, I remember constant TAC always creates problems. So you could probably disable that and so forth. Or you could also try, using a different CPU model, and explicitly enabling a few other flags and see if that's making any difference. The next is interrupt injection. So as we as we saw in the this slide, that there's a lot of back and forth going on. One of the reasons why the back and forth goes on is interrupts, right? There is an external interrupt, and then the processor jumps back to L0, the red box at the bottom, and it decides what to do with it. Sometimes it needs to inject a virtual interrupt to L1, and what happens is a lot of times due to bugs, there could be an interrupt that's actually meant for L1 and it incorrectly gets injected to L2. This is not something I'm making up because this is something actually got fixed. We had a situation where Windows was not able to boot because we were incorrectly injecting an interrupt that was meant for L1 to the Windows L2 guest, and it got fixed in this commit. And one of the other issues that is related to this is with the watchdog timer interrupts. Sometimes they also get mishandled. So you can guess if that's the case. If you disable a watchdog timer NMI watchdog on your host and then boot your nested virtualization setup and then it works, then definitely it's related to this issue. And this happens mostly with older hardware. I haven't heard of any new systems that has this, but people have seen this in the past. So spec compliance is basically doing what the spec says. So because we are almost emulating the whole the VMX environment for nested virtualization, we try to follow the spec, but sometimes just because of programmer error or something deliberate, we don't always do that. And the problem is that right now the most common hypervisor at the level 1 stage, at the middle stage, the yellow boxes, is KVM itself. And if there's some feature or there's some something that KVM does not use, those code paths don't get tested a lot because the other hypervisors KVM is the primary hypervisor that's being run as L1. So an example is MSR load store, which is basically hardware support to automatically load a list of MSRs when you enter the guest and then save them automatically when you exit it. And we didn't have that for nested virtualization for a really long time, and no one complained because everyone was using KVM as level 1 hypervisor. But then someone tried to use VirtualBox and it goes wrong. Everything goes wrong. So I think there was a patch posted for it, and it's already in KVM. I don't know if it's upstream yet. In the upstream, the kernel that Linus maintains, but it's in the KVM tree, I guess. So this is an example of that. And finally, if you get into, unfortunately, you get into one of these cases, this situation where the things don't work and none of the other cases apply to you, you could also try, experimenting with some of the module parameters that KVM has. There are a lot more, but I thought that these are the 3 that are new and mostly are probably going to, interfere with nested virtualization, mostly because of bugs or unimplemented bits. So EPT is for extended page tables, and you could disable it. You could try disabling it in actually the level 1 guest before trying to disable it in the level 0 guest. APIC V, which I think in the last presentation we saw is a very new feature, and you could try disabling that and see if that makes any difference. And a similar new feature, shadow VMCS, which lets the L1 VMCS actually access VMCSs without exits. VMCS fields without exit. You could try disabling that as well and see if that makes any difference. And if one of these things actually fixes your problem, then that's definitely a bug, or just an unimplemented feature, and you could post the list with your setup, and hopefully that will get fixed, or a patch as well. So I said I have a slide on AMD, so this is it. I just wanted to mention that on AMD we have actually, compared to Intel, we had nested disabled. Here we have nested enabled by default. So nested virtualization, you don't have to do anything in the kernel when loading the module. But we don't have a lot of changes there. Mostly the code is stable, and but we don't also have new features in the hardware. So one of them is actually APIC, which is the counterpart of APIC V, I guess, right? Yes. It's APIC V. There's actually pages on it in the AMD spec, but I mean, I don't know of any announcements to actually have it in hardware yet. So, but when it comes, of course, we have to support it. And then, trying out new hypervisors or new bugs can always, hard to find bugs can always exist, and spec compliance is also something that's kind of an ongoing work on AMD as well. So the next few slides are about some of the changes that we have to improve performance for nested virtualization. So for a while, we did not have, so just like, when EPD wasn't available for, running a guest, running a guest was slow, and people realized that. So, even for nested virt, for a while we did not expose the EPD feature to the level 1 hypervisor. So in that case, what used to happen was that, L1 is when L1 is running as a hypervisor, it's going to use shadow page tables, the old legacy way to run L2, and but L0 is going to manage its address space using EPD. So you could think of this as the translation that's going on. So this thing in the brackets is actually is the shadow mapping, and this is the whole, and then EPD is used for the mapping to the host physical address. The problem here is that this thing changes a lot. The nested guest virtual address to nested guest physical address, that is, when the level 2 guest is going to create new processes, kill them, or modify processes, clone them, whatnot. This is going to keep on changing a lot. So what happens is there are a lot of VM exits. And as I said in the first figure, the exits are always L2 to L0 and then L0 to L1, so they are very expensive. So that makes it very slow. So even if we have EPD that's actually doing a part of the translation, the gains from it are minimal because this translation doesn't change much, whereas this one does, and we are shadowing it, so it slows things down. So what we did was, we had code changes so that we let the level 2 guest actually use EPD page tables to do the nested guest physical address to the nested host physical the nested guest virtual address to nested guest physical address mapping. So this one is now taking care of the hardware, so that this is in EPD page tables. And now and L0 can use the existing shadow code to actually shadow this translation. So the advantage here is that since this one needs to change a lot, now this is being taken care of by hardware. So you don't have any VM exits anymore when this is changing. So we are not exiting from L2 anymore. And this mapping actually doesn't change much, because when new processes are created by level 2, this is something that's changing. This mapping doesn't need to change. So once once this expense has been taken care of by the shadowing structures, you can forget about it. So that's a huge performance improvement here just by using EPD for this mapping. And you could see that from some of these performance runs. You could see that without EPT, it took me 47 minutes, and it's almost like 50-60% improvement. And same for SpecGBB as well. The next.
May I ask, these are the already implemented features or features in pipeline that will be?
Nested EPT has been for a long time now. 2013. Yeah. So Shadow VMCS is basically, as I said, every time as the level 1 hypervisor is going to touch, the area that it thinks is the VMCS, we exit back to L0, and then L0 is going to actually emulate that information and write the real VMCS field and get back to running L2. So what Shadow VMCS gives us is, of course, this is a hardware. This is provided by hardware. So this is basically a virtual page that L0 can provide to L1, and L1 might think that this is actually the VMCS, and it can read and write from and write to it, and that will actually not cause a VM exit. So you are saving up on VM exits, which is of course very expensive for nested virtualization. So it gives you some performance improvement. And I do have numbers for it, but I don't think they are significant. Maybe my test cases were probably not applicable to Shadow VMCS, but you could still see an improvement. So this was 13 minutes versus 15 minutes, and SpecGBB as well. And then APIC V, it's a virtual page. Same concept as Shadow VMCS, but this applies to APIC that apply to VMCS. This is basically the guest can access the APIC without a VM exit. And this is actually more beneficial for the nested guest because nested exits are expensive. So now we expose, this is something actually in the pipeline. I don't think it's already upstream yet. It's still being reviewed, but this is basically exposing this feature to the level 2 guest so that some of the reads won't cause an VM exit. Of course, the writes do cause. And this also actually adds a bunch of other support for a bunch of other things that are actually mandatory and required for this thing to be supported, like posted interrupts and virtual interrupt delivery. And I didn't run the tests myself, but I have some upstream the author's results, and there are performance improvements here as well with W prime and iperf. And finally, this is a to-do item, nested VTD, which basically lets the level 1 guest directly assign a device from the hardware. And we don't have code for that yet, but hopefully this is something that's going to get implemented soon. We did have a Summer of Code project last year for VTD emulation in QEMU, but I think you could consider that as a foundation work, but a lot of things needs to be done here. So this is
What's the use case for this?
Graphics card inside a graphics card.
Yeah, you could think of if you want any hardware device to be used by the level 2 guest, like a network card or a graphics card, anything. And finally, as I said, VM exits is the main performance overhead. So anything that improves that, including things like adding support for newer features that are easy to just expose to the level 2 guest. Like we had recent additions to MPX and interrupt acknowledgement. So I think there could be some use cases where these kind of things actually add, speeds up things and improves performance. So with that, I have this wrap-up slide. So we know that we have up to 3 levels of nesting. We know it works, but by the time we add the 4th, I think things stop working, and no one has tried to figure out why, because who is going to want to run 4 levels? But anyway, I mean, if someone has a use case like that, and we could it'll probably get fixed. But theoretically, it should work for any number of levels. But at present, I know that people have tested 3 levels and it works. The problem with nested virtualization is it's very new, and the test matrix. I mean, if you consider every hypervisor out there and all the guests that you can think of, it's really like a huge effort, like a full-time job. So that's what is the test matrix is very complicated. And so in terms of future work, we have a lot of things that we haven't implemented fully. Like, we don't support all modes for the invalidate EPT instruction because it doesn't matter. We just invalidate everything. And we also don't have nested VPID again. This is something that doesn't matter because level 0 actually takes care of everything. But I mean, these are definitely good things to have because you want to provide a very you want to provide an environment that is more closer to the hypervisor running on top of hardware. So it's always good to have these things, and these are future scope for future work. And of course, testing other hypervisors, because most of the testing right now is, I think, KVM as a level 1 hypervisor, but I'm pretty sure if you're trying to run Windows as the level 1 hypervisor like Hyper-V, it's not going to work.
I have a question. Is it possible to migrate the guests between levels? Like from the level 2 to level 1?
Like migrate?
I tried, and it was on different computers. One was started as level, I think, 1 guest on one computer and migrated to level 2 guest on another computer without issue.
Oh,
Apparent issue.
wow.
Well, there are people that run it in their testing environment.
Yeah. Anyway, but yeah, running migrating the whole level 1 guest with its nested L2 inside it is something that I don't think works, and that's also scope for future work. There has been discussions on the list about how to do it, how to save the state and migrate it over for the level 2 guest as well. But this is still kind of future work. So that's all I had. I think I'm well before time. And these are some of the past presentations. This is nested EPT if you're interested in that. And then this is the original nested virtualization for VMX paper presented at OSDI. So that's about it. If you have any questions.
Any companies behind helping?
Yeah, Intel. Yeah. Let's see. I think there's a new. I don't know who that guy works for. I think it's a Chinese company, but they are really. He's posting a lot of patches, so definitely they're interested in it.
You find any?
I think they are. I tried going to the website. I tried to do my best to understand who that company is, but it's in Chinese. I didn't understand.
Is it Google Translate?
I tried. It's all Flash and I don't know.
Have you been approached by OpenStack at all?
Oh yeah. I mean, they do. It's. I think they're like a customer for us because they do try to use nested virtualization.
Yeah.
But they get frustrated when it doesn't work, and it's still at a stage where there's a very good chance that it won't work. But the thing I think is happening with nested virtualization is if you just get the bits right and your configuration right, and then you can forget about it. But to get to that stage, are you willing to spend that much amount of time? So that's where the real kind of hurdle is. But they do use, I think, at least try to use nested virtualization for their testing.
Did you ask about status of Intel and AMD? And from our experience with my team, as of RAN 7.0, the AMD boxes work much better in nested mode.
Yeah,
So
that's I can.
issues.
Yeah,
It's
I'm not surprised.
Performance of AMD
AMD's extensions, although they are still x86 extensions, but they are probably a little bit less complicated than VMX. So
maybe it were older Intel boxes. It were I think Nehalem boxes, not newer Westmere or Sandy Bridge. So it might be also close.
okay.
How much
Yeah.
how much does it cost in memory to have all these nested page tables? So the original page table is already 0.2%, right?
I'm not sure. No.
No. Page tables have 64-bit per unit
Yeah.
each page. So per 4 kilobytes you actually have 8 bytes.
Mm.
So but this is without any virtualization. No. So if you have a guest, you have 2 sets of tables.
Right. I mean, that's true, but I think if you look in that sense, I mean, memory is cheap now. But yeah, you do have to have those. I mean, if you want performance, then you need more money and buy more memory. Yeah.
How about other architectures?
Oh yeah. We are still kind of talking about, this is all myth about things we could do to support nested virt on ARM, but
I would guess that S390, for example, supports steady hardware. The code for that would come from IBM, right?
I'm sorry.
S390?
Yeah, S390.
They probably have hardware support for that?
Yeah, it looks like and I think Drew just told me that even ARM has started to do something like that. So
ARM64, right?
yeah. So looks like theoretically it should just work because that's how you could just extend it to the upper levels. But I don't know. No one has tried it yet. I don't have the hardware for that. Yeah.
Have you, what is the impact on I/O?
Oh yeah, definitely. I completely skipped that.
Yeah.
Nested has a lot of things. Like the nested file system itself is going to make things slow. I think there is impact on I/O, but if you just using standard virt I/O devices, it's the truth is that I probably haven't focused much on I/O. It's more kind of CPU performance, but I'm definitely sure that's something we have to. That's the next step. Yeah, exactly.
Stabilize the CPU.
That's true. Yeah. Okay. Thank you. Yeah, I did. Oh.